The Great Divide, a tale of three hardware emulation architectures. Hardware emulation arose as a necessity out of the needs of the 80s. By mid-the 1980s, semiconductor design had outgrown the practical limits of the gate-level simulation. Gate-level simulation delivered accuracy, but the glacier place silicon prototypes performed at real speed but arrived fault rate. The industry needed a new instrument, a verification engine capable of executing the real hardware models at a meaningful speed while preserving the feasibility and control required to follow through the verification. Hardware emulation was born to fill that gap. Who would have thought of that time that Moore's law of complexity growth would be so dramatically outgrown by AI model complexity around the 2020s? Well, hindsight of the 2020, as we know, let's take a look at what actually happened with semiconductor demand. Figure 1. Semiconductor demand acceleration. Source synopsis. Through 4 generations of major electronic system eras, PC, Internet, mobile, IoT, and cloud, one can argue the evolution of emulation was driven by the different paradigm fighting for market share through a different balance of technology advances. Serving a very broad market requirement, today's market is primarily investing in AI chips which must execute the AI models with explosive complexity growth. It is not a surprise that emulation architecture with performance advantage for executing these long AI workloads are today winners in the market. Let's visit the journey of how the old emulation technology evolved and how commercial FPGA-based architecture came out on top for today's need for AI system verification. The first generation of the emulators relied on the best of the areas of the commercial FPGAs, a radical leap forward at the time. These systems enabled pre-silicon validation of complex chips that would otherwise have required years of simulation alone. For nearly a decade, the process followed a predictable trajectory. Each new generation of FPGA devices delivered greater capacity, higher performance, and the ability to map the increasingly ambitious design. So the scale improved dramatically, but the underlying philosophies remained largely unchanged. As these platforms grew, however, their limitations became impossible to ignore. Increased logic capacity did not resolve the architecture constraints embedded in their foundation. Early FPGA-based systems carried out many engineers would later describe as their original sins. The sheer number of the FPGAs required to keep pace with the exploding design sizes drove setup times into weeks and even months. The compilation cycles stretched into days, often delaying the TLDs beyond the project schedules and making iterative development painfully slow. Design feasibility was equally strained. Internal adaptability depended on a compile probes into fabric, consumed valuable resources, increasing routing congestion, and turning debug into a laborious exercise. Execution models were rigid, centered entirely on the in-circuit emulation, as in limiting flexibility for inactivity, debugging, and of total cost of the ownership, purchase, and operation and maintenance, placed these systems fall beyond the reach of the most engineering teams. As a result, hardware emulation remained confined to the most critical verification challenges, so typically late in the design side within only the most advanced organization. For many teams, it was not a day-to-day engineering platform, but a scarce, high-value resource, powerful and indispensable and perpetual in short supply. The seeds of a great divide were beginning to grow. By mid-1990s, the commercial landscape appeared stable to the surface, dominated by the two primary players, QuickTurn design system, and the ecosystem. Yet benefit the stability, the field was undergoing a profound transformation. Designs were scaling rapidly, and software stacks were growing alongside hardware complexity, and verification demands were shifting from the block level correctness to full system behavior. The question was not longer whether the emulation could scale the accordingly, but how. Out of these pressures emerged the fundamentally divergence in architectural thinking. Vendors and the engineering teams began reimagining and what an emulator should be. Not just a large FPGA array, but a purpose-built verification instrument optimization for visibility and so controllability of system-level performance. This thinking gave a right to the three distinct hardware emulation architectures, each grounded in a different philosophy, each making different trade-offs in speed, scalability, and usability, and each shaping the trajectory of the silicon verification to dedicate that to for decades to come. The three architectural approaches that emerged came to the known as processor-based emulation, custom FPGA-based emulation, and commercial FPGA-based emulation. Each representation a distinct attempt to overcome the growing limitation of simulation while enabling hardware design to be validated at meaningful speed and scale. The essential characteristics of this technology can be understood by examining their origin, evolution, and practical trade-off. The process-based emulation. IBM the emergence of the processor-style approaches. In the early 1980s, IBM began to explore hardware acceleration techniques to improve design verification efficiency through the project such as Yorktown Simulation Engine, YSE, and the Engineering Verification Engine, EVE. These systems functioned as a simulator accelerator, special-purpose computing platform designed to execute the hardware description expressed in software language more quickly than the conventional simulators. While they deliver a measurable speed improvement, they still fell short of the performance required to apply real-world scenarios to the design under test (DUT). By the mid-1990s, the IBM had refined a new architectural direction centered on a range of simple Boolean processors. These processors operated on the design and data structure stored in large and shared memory and were coordinated by the sophisticated scheduling mechanisms. The approach proved adaptable to full emulation workload, offering a scalability alternative to traditional simulation. Still, IBM did not capitalize on the technology. So the QuickTurn and the commercialization of the processor-based emulations. After nearly a decade of experience with the commercial FPGA-based emulation systems, QuickTurn reckoned that the design, despite the important advances and the simulations emulators reveal and structural limitation that improved the difficult to overcome, achieving the sufficient design capacity required interconnecting hundreds of FPGAs across the multiple boards, creating significant logistical and engineering challenges. Partitioning routing designs across the distributed fabric often needed months of preparation to avoid congestion and ensure deterministic behavior. Debugging visibility had to be explicitly compiled into the design and competing with the routing sources and slowing development cycles. The performance also failed to scale linearly with the design size, with the execution speed declining as workloads grew more complex. In search of solutions, QuickTurn evaluated a custom FPGA architecture developed by a French startup by the name of the Meta system. At the same time, Meta Graphics, after abandoning early experimentation with emulation and selling all assets to the QuickTurn, pursued the same path. The resulting as the competition escalated into legal dispute over intellectual property, ultimately culminating the vendor's acquisition of Meta system. The QuickTurn, already familiar with the IBM processor-based work, moved decisively in that direction rather than commercializing the technology directly. IBM entered into an exclusive OEM agreement with the QuickTurn, enabled the latter to incorporate the architecture into a new generation of emulation systems. IBM processor-centric architecture offered a compelling alternative. It addressed three of the most persistent constraints associated with FPGA-based systems: lengthy and setup and compilation cycles, restricted debugging visibility, and performance degradation at a large scale. One drawback, less visual at the time, was higher power consumptions compared with the FPGA-based solutions of equivalent capacity. So, in 1997, the QuickTurn acquired the IBM technology and soon after introduced the concurrent broadcast array logic technology, Cobalt Emulator, the first major commercial platform built on a processor-style architecture. The product achieved rapid market acceptance. The competitive landscape continued to shift. Ongoing litigation between the Mentor and QuickTurn persisted until around 2002, when Cadence acquired QuickTurn and resolving this dispute and consolidating the key emulation technology with its portfolio. The cadence and the scaling of the processor-based emulation. Following the acquisition, the Cadence phases out QuickTurn's FPGA-based product lines and committed fully to processor-based paradigm. This decision laid the foundation for the long evolution of the Palladium family of emulators, which became the company's flagship platform. Successive generations introduced from the early 2000s onward, the Palladium preserved its fundamental architectural principle, large array of the simple processes working in concert to emulate the hardware behavior at scale. With each iteration, design capacity expanded, execution performance improved, debug capabilities become more comprehensive, and compilation workflows grew faster and increasingly automated. So two characteristics consistently define the appeal of the platform. First, compilation time was significantly shorter than those associated with the FPGA-based approaches, enabling faster turnaround during development. Second, the engineers benefited from the full design visibility at runtime without requiring special compilation steps, a powerful advantage for debugging and iterative verification. So the Palladium also provided a particular strong in the in-circuit emulation, a broad ecosystem of the speed bridges enabled direct directions with the real hardware interfaces, allowing the software and the hardware to be validated together in realistic operating conditions. These strengths were accompanied by the structural trade-offs. Processor-based systems require substantial physical infrastructures and typically consumed more power than FPGA-based emulators and comparable capacity. Customers had to invest into a costly water cooling infrastructure. Scaling to multi-billion gate design often demanded larger installation composed of the numerous cabinets. In transition-based acceleration scenarios, processor-based platforms also tend to operate at lower execution speeds, and the competing architectures optimized specifically for that use case. Despite these constraints, processor-based emulation established itself a foundational technology and hardware verification, offering a unique balance of the scalability, visibility, and productivity that continue to shape modern emulation platforms. The custom FPGA-based emulator. Custom FPGA is a parallel innovation path. While IBM was advanced processor-based emulation in the United States, a parallel and equally important line of innovation was taking shape in Europe. In France, the Meta system has been developing a class of the programmable silicon inspired by the field programmable gate array, but engineered specifically for emulation workloads. These devices, often referred to as custom FPGAs, were not intended for general logic prototyping or ASIC design. They were purpose-built as a computational fabric of an emulator. Unlike commercial FPGAs, whose architectures must accommodate a broad range of applications, Meta systems programmable devices were optimized for the specific requirements of hardware verification. Their architecture combined configurable logic elements with dense and deterministic interconnected metrics tailored for predictable timing. Embedded multi-memories enabled efficient storage of design state and stimulus data, while high-bandwidth I/O channels supported the connection to the external systems and software environments. The device also incorporated built-in debugging engine, including memory device proving capabilities and dedicated clock generation circuitry to maintain the synchronization across a large MFT design. This specialization yielded several tangible benefits. Compilation and startup times were dramatically reduced because the routing and configuration problem was constrained and optimized for the emulation rather than general synthesis. Designers gained full visibility into the design and during the execution, often without a need for lengthy compilation cycles to insert proofs. And the designs grew in complexity, performance scaled more predictably, because the architecture has been engineered around the structural characteristics of emulated hardware rather than generic programmability. Compared to the processor-based emulator, the custom FPGA approach delivers a similar functional capability with a low power consumption and a more hardware-centric execution model. So mental graphics and commercialized of the emulator on chip. The premise of the custom FPGA-based emulation was attractive industry attention. In 1996, the maneuvering the QuickTime, the mental graphics acquired Meta Systems and introduced Sim Express, the first commercial emulator built around the customer programmable silicon. Sim Express was, in many respects, a proof of the concept rather than a fully competitive platform. Housed in a compact chassis roughly the size of a small wine cellar, it mapped the designs of the fewer than 100,000 gates at a time, and when the leading ASICs were already exceeding the emulation gate threshold. Yet its architectural direction was significant. Setup was simpler. Compilation times were reduced from hours to minutes. At runtime visibility, the design was far superior to what many FPGA-based systems offered. The platform demonstrated how emulation optimized silicon, paired with the advanced verification software, could form a balanced environment for pre-silicon validation. The mentor expanded its concept to the introduction of the CelluLO in 1999, a substantially large emulator, a normal capacity of approximately 5 million gates. By clustering the multiple systems, engineers could scale the total capacity beyond the 20 million gates, an important milestone as the system on chip SoC design grew rapidly in size and complexity. So the custom FPGA approaches, however, came to the trade-off because these devices did not match the raw logic density of the largest commercial FPGAs. More chips were required to implement large designs. Larger array meant longer interconnect paths and increased signal propagation delays. As a result, the execution speeds often fell below the 1 MHz for large configuration. Adequate verification workflow, but slower than competing FPGA-based emulators at equivalent capacity. The ICOs and virtual wires and transaction-based verifications. A favorable shift occurred in 2002 when Mentor Graphics acquired ICOS system. This acquisition brought two complementary technologies that would shape the next generation of emulation. The first was virtual wire interconnect methodology, originally developed via the Virtual Computer Corporation (VCC) and later incorporated into ICOS platforms. Virtual wire simplified the daunting task for the routing large designs across the many programmable devices by the isolation of physical connectivity into software-controlled interconnect layer. Engineers could reassign their signal paths without physically rewiring pods, dramatically accelerating bring-up and iteration. The second was ICOS work with transaction-based verification. Rather than exchanging the low-level signal toggles between the test bench and the hardware models, the methodology elevated communication to higher level transactions, data package, protocol event, and software interactions. This approach significantly improved the verification efficiency and enabled tighter coupling between the hardware and software validation. Mentor integrated these innovations into a virtual emulation family, first introduced in 2007, and positioned as a new generation of the emulator on-chip systems. The architecture combined a custom programmable silicon and a scalable interconnect and advanced verification software into a unified hardware-assisted verification platform. The differentiated through the verification methodology. Well, the Mentor ultimately distinguished itself was not only hardware and in methodology. Building ICOS foundation, the company introduced Test Bench Express TBX, widely regarded as one of the most effective implementations of the transition level acceleration. TBX enabled software branches, typically written in system Verilog C or the system C, to execute efficiently alongside the emulated hardware by offloading transaction handling to the most host environment. The mentor expanded this approach further with the virtual lab, a suite of the application-specific verification environments tailored to industry protocols such as USB, Ethernet, and storage interfaces. This environment allows the team to validate real-world workloads and software tracks earlier in the design cycle, bridging the gap between the silicon hardware verification and the system validation. Evolution to a Verilog family. Over the following years, the Verilog platform progressed through the multiple generations. Each iteration increased design capacity, improved execution performance, and enhanced analysis capabilities. New features supported low-power verification, power estimation, and hybrid emulation with virtual platform, and functional coverage analysis. The systems evolved from the niche verification engines into a central pillar of the hardware-assisted verification strategy for large SoC. In 2018, Siemens Digital Industry Software acquired Mentor's Graphics and incorporated the Verilog product line into its broader electronic design automation portfolio. The development continues with the platform adapting the demands of the billion-gate designs, complex software stacks, and heterogeneous computer architectures. Today, the latest generation of this lineage in the Verilog Strato CS, part of the Verilog CS hardware-assisted verification platform, is representing the culmination of a decade of the architectural revolution from a custom programmable silicon and virtual wire interconnected by transition acceleration and enterprise-scale emulation infrastructure designed to support the verification of the modern AI-driven, software-defined system on chips. The FPGA renaissance. While processor-based and custom FPGA-based emulations were establishing themselves in the market, a parallel transformation was unfolding in programmable logic. By the late 1990s, the new FPGA generation from the Xilinx and Altair began to close long-standing gaps in density, speed, and routing flexibility. Devices could now lose a significantly larger portion of the non-popular system on chip SoC designed, while the improved place and route and root tools shortened the iteration cycles, an essential requirement for verification teams working under relentless tape-out pressure. Around the turn of the millennium, Xilinx introduced the Vertex family, making a new pivotal inflection point. These devices combined the higher logic capacity with faster interconnect and crucial read-back capabilities. Engineers could inspect internal registers and memory content at runtime without recompiling the design. The trade-off was performance. Read-back operations slowed execution, but the feasibility they enabled proved invaluable for debugging complex systems. For verification engineers, this represented a new balance between the observability and speed, one that would shape FPGA-based emulation strategy for years to come. The rapid progress of the commercial FPGAs reignited interest in building the emulators directly from off-the-shelf programmable devices compared to the custom silicon approaches. FPGA-based system promises faster innovation cycles and lower development cost, while benefit from the continuous performance gain delivered by the FPGA vendors. This environment is set to the stage for a new wave of the entrepreneurial activity. The two startups operating on opposite sides of the Atlantic capitalized on this opportunity, each pursuing a distinct architectural philosophy. In Silicon Valley, in 1999, Axis introduced a simulator accelerator based on a patented reconfigurable computing RCC architecture implemented as a range of FPGA in the system market under the name Excite, initially targeted acceleration of the simulation workload rather than a full emulation. Within a couple of years, Excite evolved into Extreme and more traditional emulation platform. One of Extreme's defining innovation was the hot swap capability, which allowed the engineers to move designs seamlessly between the emulator and the proprietary simulator. This approach leverages the interaction debugging strengths of software simulation while retaining the speed advantages of the hardware execution, the bridging the two previously distinct verification domains. At roughly the same time in Europe, a more disruptive initiative was taking shape. Emulation verification engineering, EVE, founded in 2000 by four former amateur graphics engineers, set out to rethinking the FPGA-based emulation from the ground up. In 2003, the company introduced the JIBU, Jitterbugs, an emulator implemented a compact PC card. The first version, JIBU GV, incorporated two Giants Vertex 2 devices and one dedicated to the mapping the design under task DUT and the other tasks with accelerating transaction level executing through a newly conceivably configurable test bench RTB technology. This architectural decision proved pivotal. By elaborating the test bench to the hardware enabling transaction level verification, JIB significantly increased the throughput, reduced communication bottleneck between the DUT and verification environment. At the same time, the system leverages the Vertex readback features to deliver runtime visibility into internal state without recompilation, so again, trading the execution speed for the powerful debugging capabilities. The concept demonstration both technical feasibility and commercial promise. Within a year, EVE extended the architecture into a chassis configurable with a range of Vertex FPGAs. The resulting system, JIBU XL, marked the transition from a compact and personal emulator to a scalable enterprise emulator platform. Over time, the product line evolved through the successive generations, and each benefited from the advances in FPGA density, clocking, and tool automation. A major milestone arrived in 2009 at the DAC with the introduction of the chip server, the progenitor of the long-lived product family, designed for scalability from a single chassis to multi-rack configuration. JIBU server could not normally capacities of 1 million gates, and it introduced a higher level of automation, including the incremental compilation, faster places and routing cycles, and multi-user capabilities, features that are reflected of growing industrialization of the verification workloads. Equally important were its economy and operational characteristics. JIBU server delivered a greater execution speed than our competing emulators while consuming a fraction of their power of computing. Its pricing reportedly dropping below penny per gate in large configuration, reset expectation for cost efficiency in hardware emulation. The platform quickly gained recognition for offering one of the lowest total cost of ownership in the industry, positioning EVE as a formidable player in the verification market. So architecture JIBU also departed from the prevailing in-circuit emulation mindset. Early system emphasized transition-based verification through the RTB, later renamed Flexible Test Bench (FTB), operating at higher scale-lock speed than a DUT to maximize bandwidth and responsiveness. As the capabilities were introduced in the late generations, but the transaction level acceleration remained a defining strength, aligning with the increasing role of the embedded software and system-level validation. So Synopsys moves into emulation. The growing relevance of the hardware emulation did not go unnoticed by the major EDA vendors. Synopsys recognizing the strategic importance of the technology as early as the mid-1990s, attempt to enter the market through the acquisition of a startup named Arcus, which had developed processor-style emulation approaches. The effort proved unsuccessful, and within months, the Synopsys divested the company and its asset, which were subsequently acquired by the QuickTime. The early setback delays Synopsys' direct involvement in emulation in more than a decade. During this period, the market matured, the FPGA-based solutions gained creditably, and the system-level verification requirements identified, driven by the rise of complex SoCs and embedded software stacks. The turning point came in 2012, when Synopsys acquired EVE. By then, the EVE was already delivering the third generation of a Jeeves server platform with a highly established reputation for performance and scalability and cost efficiency. The following the acquisition, the Synopsys invested heavily in advancing the Jeeves roadmap. The capacity continued to scale, performance improved, and the compilation time shortened through the enhanced automation and tool integration. New analysis and use modes were introduced, supporting everything from software bring-up to system validation and hybrid prototyping. This development cemented commercial FPGA-based emulation as a long-term pillar on our verification landscape. So now summary. What began in the mid-1990s as the programmatic use of the rapidly advanced programmable logic was evolved into a cornerstone of the modern semiconductor development, scaling to the multi-billion gate designs, enabling software-defined systems and supporting the increasingly system-centric nature of verification. At its core, the evolution of the hardware emulation is a story of the architectural divergence. The three distinct approaches emerged, each shaped by the technological constraint verification demand of its time, and each redefined what emulation platform could deliver. The early dependencies on commercial FPGAs exposed the fundamental mismatches between the available technology and the requirement of the system verification. And the realization marked a turning point, giving rise to the processor-based and custom FPGA-based architectures to powerful but fundamentally different paths to sustain the emulation through a decade of explosive semiconductor growth. Their later disruption by a new generation of FPGA-driven systems did not render earlier approaches to obsolete. Instead, it broadened the architectural landscape, underscoring a critical truth: the single emulation architecture can optimally address every verification challenge. Over time, the role of emulation has expanded dramatically, driven by the convergence of evolving user demands and the advancing technology. In the AI era, verification has become fully system-centric, requiring the execution of massive software workloads, such as the large language models. In the next generation architecture, the shift places three factors at the center of emulation: effectiveness and system capacity, execution performance, and interface connectivity. On the right balance of all three enables meaningful polysilicon validation at scale. Among today's competing approaches, commercial FPGA-based platforms are best positioned to deliver across all three dimensions, offering a compelling balance of scalability, speed, and real-world the interfacing that allows and with the needs of modern AI system development. Okay, I like this article with. Thank you. Thank you for your time. See you next time.